after after I attended this morning the lecture of Bill and talked to Pierre a little bit, I changed my plan basically completely from what I'm going to talk about. And I will still try to give 2 lectures on quantum controls of spins and photons, but basically what I will try to do is I will try to kind of today give a lot of background, some kind of very basic stuff that we're kind of teaching in our graduate courses, but I will try, as much as the time allows, then make connection between this kind of very basic concepts of coherence and decoherence and open systems with the stuff that we are actually doing in the lab now. So here is basically what used to be my plan, but we will see how it goes. So today I'd like to focus on physics of atom-like systems in a solid state. And I'd like to start out by just a very general perspective talking about quantum coherence in open systems, and then move on to describe what we mean by these atom-like systems, which are basically impurities in solid state, and then apply some of these ideas of open systems to the problem of spinning qubits and the decoherence in a solid state. And then, if time allows, I'd like to talk about some examples of the current research. So I will talk about how we can use the techniques and tools of atomic physics for real-time observation and control of the environment of solid-state qubit. So in this case, environment will be composed of nuclear spins. I will perhaps talk about some applications of these techniques and tools for magnetic sensing, particularly magnetic sensing at nanoscale, and just in some kind of, in case I don't run out of time by then, I will talk about some very recent work in which we are trying to push the limits of the solid-state quantum memory, and it might have some application to something which is called quantum mine. So, just to start with, this work is a part of the broad effort which now spans several disciplines of physical science, and this is an effort to control what is sometimes called controlling quantum. So in this effort, what we are trying to do is we are trying to isolate and control simple quantum objects first. So single photons, single atoms, single spins, and so on. And then once we obtain the control over these simple quantum objects, we would like to use them to start building more and more complex systems from them. And what we would like to do is we would like to kind of study new physics with this kind of engineered quantum systems. For example, try to look for new states of matter, the states of matter which do not exist otherwise in the real world, or perhaps explore some potential applications of these techniques. And of course, one of the most famous applications is the quantum information science. So this topic actually emerged as one of the most exciting topics in the physical science. But at the same time, it is also clear that building useful and controllable quantum systems using this approach is actually extremely challenging. So I'd like to illustrate why this is challenging, and I'd like to illustrate it using an example of building a quantum computer. So in principle, we know all what it takes to build a quantum computer. For example, there are now textbooks where we can just open and read all of the requirements. Yet, this is very, very difficult. Why is that? So basically, what we need to build a quantum computer is something which is called quantum bits, which is two-level systems. For example, spin 1/2 is a quantum bit. We can call the classical bit of information, but also quantum bit. We can put the system in a superposition state. And then we need some sort of quantum wires. By quantum wires, I mean some kind of quantum channels which can be used to connect these quantum bits together in a kind of coherent quantum mechanical way. So, okay, that's the basic ingredients. So what is so difficult about this task computer, quantum computer? So the first challenge is that these quantum bits have to be very well isolated. So they should be able to preserve quantum mechanical superposition states for very long periods of time. Okay, that's already challenging, but you know that as you will see, we're actually making a lot of progress towards that, so this is actually possible to do. So this isolation means in particular that the interaction between these qubits and other qubits, and as well as surrounding world, should be fully coherent and controlled. We should be able to really basically, you know, turn these interactions on and off at will. And then once you achieve this kind of situation, all what it takes is basically just to build a quantum computer is basically just keep adding these qubits. So, and if you add these qubits, you of course will need to wire them up, and this is the subject of quantum wires, so quantum channels, which you need to use to basically, you know, couple these qubits to each other. So essentially, the key challenge which the researchers in this field are facing is the challenge of simultaneous isolation and control of what amounts to a many-body system. So basically, on one hand, we need to be able to isolate these qubits. We really keep them coherent for a long time. But at the same time, we really need to control them with exquisite precision. And we need to do it not just with one qubit, but with the whole bunch of those. Right? And that's what turns out to be a very challenging task. So here are some examples of the current research directions which are being pursued in this field. So on one hand, there are by now a couple of what I would call advanced qubit systems, for example, trap lines or Josephson junctions, where one can actually control, you know, several of such qubits at once. You know, several, you know, means starting from 2 and going up to maybe a dozen or so. And you know, with these systems, one can already implement some simple quantum algorithms, do some kind of simple quantum computation. At the same time, there is still a very active search ongoing. This is a search for new qubits. So it turns out that, you know, no matter which specific qubit implementation you look at, you can immediately realize that it has some big advantages, but also it has some, you know, disadvantages. For example, for some systems, it's very easy to isolate and control, you know, 1 or 2 qubits, but, you know, scaling them to larger systems appears very challenging. At the same time, for the other kinds of qubits, like photons, for example, you can use them for transmitting quantum information very well, but, you know, you can not use them for storing information for very long time. So basically, you know, these two subfields essentially involve, on one hand, looking for new qubits, which could perhaps combine the advantages of various kinds of systems. Or, on the other hand, you know, if one cannot find one ideal perfect qubit, perhaps an approach might be possible in which you basically put different qubits of different kinds, which are good at different tasks, together to try to basically explore some kind of hybrid quantum system. And finally, as I already mentioned, there are now some physical systems in which you can actually control, you know, few qubits at the same time. So the question is arising whether one can already use this kind of systems to study new physics, or perhaps, you know, explore some kind of new applications. And this is research for useful applications of small-scale quantum systems. Okay, so this is kind of a general introduction. So against this backdrop, what I'd like to do today is talk about the use of the so-called atom-like systems, which are basically an isolated, localized systems in a solid state. And I will argue that, you know, they have some advantages because, you know, sort of they are stable, and we learn now how to control these systems. But of course, you know, in contrast, for example, with cold atoms, the kinds of things that Bill or June talked about earlier this week, they are not exactly isolated, right? So they exist within a solid state environment, and they interact with this solid state environment. So in that sense, one of the central challenges, you know, once one looks at this kind of systems is, you know, to what extent they can preserve their coherence. So this will be a major part of today's lecture. And what I'd like to start with is I'd like to start by giving you some background about, you know, sort of open quantum systems and, you know, and kind of some general notions of how one can describe and understand, the coherence in such a system. So, and I'd like to do it actually using the blackboard. So this is kind of unconventional technique so far in this school, but perhaps you will appreciate it.
Most controllable.
It's the most controllable and time-proven method. Okay, so what I'd like to do is basically now talk a little bit about open quantum systems, and I must say immediately that the discussion here will follow the lecture notes in the class that I'm teaching at Harvard. So there is a website here, and you can actually download some of these lecture notes tonight. So in particular, this is chapter 3. So basically, in general, if we talk about some specific quantum system being a single atom, or in our case it will be a single spin, for example, in practice they can never be considered in isolation. They always interact with the environment. So this interaction can be strong, weak, it can be at different time, but this interaction is always present. So for this reason, in quantum optics, for example, we often talk about open quantum systems. So basically, generically, we consider a situation where we have a system of interest that we would like to control somehow. But this system now is not completely isolated. It interacts with something which we are going to call environment. So by environment, we mean some kind of other quantum system which has many degrees of freedom, which generally is difficult to control. And the interaction between two will be described by some kind of generic Hamiltonian. So these are some operators which belong to the system, and these some operators which belong to the environment. So the problem and kind of the main challenge in this field is that due to the interaction, due to this kind of interaction, the system, as the time progresses, becomes correlated with the environment, or as people often say, become entangled with the environment. So for this reason, if you, for example, look at certain degree of freedom of the system, at some point after a certain evolution, this degree of freedom does not, often sort of does not correspond to kind of a pure state of the system. So due to this entanglement, effectively, the state of this system becomes a mix. So what sort of questions and goals do we pursue in this context? So one of them is, of course, the question of how can we keep the system coherent. Right? What can we do? And so, and the mechanisms here is, of course, we clearly can try to do, something on our system, like shine a laser light on our system, or shine some kind of radio frequency pulses. We can also try to do something with environment. So environment is a kind of big and messy things, but perhaps there might be some method where we can exhibit at least some degree of the control over this environment. So, okay, so this is basically the first basic question, how to keep the system coherent. That's a question number one. Of course, there are some other related questions. So, for example, if you look at some degree of freedom, which is extremely well isolated, it can store coherence for a very long time, but in practice, this coherence might not be very useful unless we can actually access the system, unless we can prepare the system in a well-described state and we can measure it. So basically, the second kind of question which we often ask is how we can measure our system once again in the presence of this environment. And then there are, of course, other questions. So, for example, we might want to make this system interact with other systems, or we can make this system interact with some other external perturbation. For example, if we want to make a measurement device out of this system, for example, a device which measures time, or measures external electric or magnetic field, we would like to actually make the system to be sensitive to the quantity we want to measure, but while trying to decouple it from the environment. So this is the third kind of set of questions: how we can make our system sensitive to some perturbations while sort of keeping it isolated from the environment. Okay, so these are the kinds of questions which in general researchers are interested in. Okay, so this is sort of a general setting. So how can we analyze the dynamics of this open quantum system? So once again, in general, what we could say is that suppose that at some point when the time equals 0, we can prepare our system in a pure state. And then at time equals 0, the total state describing system and environment can be written as this kind of product state, maybe in a kind of more general sense in the density matrix. Using density matrix, we can write it like this. Right, so the key thing is that at this point, this is a pure state. Right, so the state of our system is totally decorrelated from the environment. But then, what will happen is that as we let the time evolve, due to this kind of interaction in general, our system will become correlated with the environment. And so what will happen is that the wave function will in general can be written as some kind of constants times the product of the system and the environment state. So suppose this is now basically a product state basis, where this is a basis in the system subspace is environment subspace, and I can always write my state in this kind of way. So if you are now interested in the degrees of freedom of your system alone, then what you should do, you should try to find the density matrix, the reduced density matrix of the system. So let me just actually pause now. So who knows, who has heard about the concept of reduced density matrix? That's good. So, okay, so how do we find it? So the question is, how do you find the reduced density matrix? Exactly. So basically what you do then is, if you want to find the system density matrix, what you do, you just basically trace over your environmental degree of freedom, and then the thing that you trace is this thing. And in general, if you have a state like this, if you go through some lines of algebra, basically what you find is that your state of the system will be described by this expression. So this is, in the case when there's several of these coefficients non-zero, this is no longer a pure state. Right? This describes the statistical mixture of this. So what this means is that original pure state will lose its coherence, right? So it will become a mixed. So this is, a very general kind of statement. One could argue whether it's useful or not, but that's what always happens. So for the purposes of today's lecture, what I'd like to do now is kind of go, while still keeping this discussion general, I'd like to kind of go one step deeper into this process of system-environment correlation, and I'd like to talk a little bit about the properties of different environments. Specifically, I'd like to talk about, how the, sort of the time dynamics of how the state evolves from this state to this state. So it turns out that one key property of environment which plays an important role, a very important role in this process, is something which is called correlation time. So in these kinds of problems, when we are thinking about the system-environment interaction, we often think about a system being something kind of small and insignificant in terms of like a global universe. Environment is kind of big and humongous, so environment basically lives its own life, and it just, occasionally, does something to the system, but, this something is very damaging, so it's not pleasant. We don't want it to happen. So basically, the correlation time is kind of an intrinsic property of the environment. So it basically determines how fast does environment evolve on the time scale of our interest. So to be specific, let me consider kind of the simplest possible quantum system, and this is basically an example. The example will be spin 1/2 in an external magnetic field. And let me consider the situation where this magnetic field is oriented in the z direction. And so in general, this magnetic field can be sort of a quantum degree of freedom. So it can represent some sort of environment. So, and of course what the spin will do now is will precess in this kind of magnetic field. So the situation which I'd like to consider is a situation where this quantity somehow evolves in time. So this evolution might be caused by different factors, and as I mentioned already, that in principle this B can be an operator, but to simplify the discussion and to really kind of bring it to the kind of very simple terms, I actually would like to just consider this B for now as being a classical field. But I'd like this classical field to somehow mimic the properties of the environment, and for this reason I will choose this classical field to be basically a random variable. So let's consider the situation, a random variable which actually also depends on time. Okay? So to specify the model, let us consider the following. So let's consider this B as a classical random variable which in addition we will assume to be kind of described by Gaussian distribution. So is this concept familiar for everyone? So what does it mean if you have a random process which has a Gaussian distribution? What does it mean? What?
Use a Gaussian distribution.
Exactly. So basically what it means is that you have some kind of, have a set of kind of, things, of outcomes, and basically, you can only predict statistically what will happen. So, and basically the distribution, probability distribution of different outcomes will be Gaussian. So the reason why Gaussian distributions are convenient is because they can be quantified by just two numbers, right? One of them is an average, and another one is basically a second, is a variance in the second order moment. So, and in our case, we will just assume that the average over all realization of the stochastic processes will be 0, but the second moment will not be 0, and in addition will be characterized by some correlation function, which I would like to write in this kind of form. Okay, so what does it mean here? So first of all, what is this average over? So this is not a quantum mechanical average. This is an average over this kind of classical random process, right? What do I see of classical? And so the second order moment here is the only non-trivial thing. And what I like to kind of indicate is that the second order moment, and the result, the entire random process, is quantified by two things. One is basically the magnitude of this fluctuation. So this is, for example, kind of an average, value of this kind of the variance of this field. And the second thing is a time-dependent function. So this term basically quantifies what we would call correlation properties of this random process. So by definition, we can set f of 0 to be equals 1, right? So that basically, when times are equal, we just get this, kind of the strength of these fluctuations. But then, eventually, when this time difference goes to infinity, presumably the process is totally random, then, basically this quantity should be 0, because if something happened, a million years ago, should really have not much, effect on what is happening now, right? But so then the only thing which this term will give us is a time scale. And this will be this time scale which I will call the correlation time. So this is basically Tc is a time scale over which this function basically goes from 1 into 0. So this is f of tau versus tau. So Tc will be the decay of this correlation. Yes?
What is the motivation behind choosing f linear function of t minus t prime as opposed to something else?
That's a very good question. So there is another assumption which I made here, and I made an assumption that this process is stationary. That nothing, that sort of, no matter whether I started now or started a year later, the kind of, on the average, the characteristics will be the same, and this automatically guarantees that the view will only depend on this time. Okay, so the setup of this problem kind of looks a little bit artificial, I must admit, but but this is something I would call a kind of two-level system, of the coherence physics, right? Because it turns out that this kind of very simple model really contains a lot of essential ingredients, which turn out to will be true in a much more general setting. It will be true in the case when B is an operator. It will be true when this system is not just one spin but many, etc. So if we can understand what is happening here, then 90% of my mission is accomplished. Okay, are there any questions about the model?
You are modeling the environment by the SD.
Exactly. And I kind of treat it, I treat it really now as a classical factor, but it turns out that in many cases, even if it's a quantum field, this description will be effectively valid. Because, for example, if this quantity, if both of these quantities are kind of integrals of motion, then, with respect to this interaction, then this model will be valid. But we will see quantum examples which will map exactly on this. Any other questions? All right, so let's now try to find out what's what.
Can I just make a quick comment? Would you mind writing closer to the the top of the board, so each one is that.
Sort of exploring the possibilities to lift it, but it's not so easy. Yes, I will try. Yes, I will try. Yes. The board has a limited space. So. All right, so let's now, we have defined the model, so let's now try to find out what will happen with spin. What will be the spin dynamics within this model? And the first question which I'd like to ask is what will happen with the z component of this spin? Is it going to change? Any thoughts? What? So what will happen with Sz exactly, with an operator Sz? So is it going to change in time? So what's going to be the time derivative? Exactly. What's going to be?
Minus Sc.
Yeah. And what's it going to be? Okay. So I want answer. I want a number or the expression. I know how to calculate it. I want an answer.
It's going to be 0.
It's going to be 0. Why? Because? Commutes with this Hamiltonian. Exactly right. Okay, so let's now, it's good. So let's try to now find some, let's try to look for evolution, for example, of S plus. S plus is a rising operator, right? So basically if our spin states are, say, spin down and spin up, then F plus is just takes us from the state down and brings us to the state. So what's going to be the evolution of S plus? It's going to be also 0.
S plus only S minus.
So what's going to happen here? So what's a commutator of a z with S plus? Thoughts? Come on, guys. This will get very complicated very quickly. So this is a chance. So all you need to do is to calculate the commutator S plus with z, and the z is just basically up, up, minus down, down. So, okay, I'm going to write down the answer that I want to get, and the question is it right or not? So it will only depend on S plus. Is it correct? So the reason why this is actually a very nice equation is because one, of course, can integrate it directly, right? And what it means is that we can solve explicitly. We can basically integrate this equation and find exactly how does S plus operator with the wall. Okay, so in atomic physics, we don't, always, kind of solve these equations when we think about that. And that's where the concept of Bloch vector and Bloch sphere is extremely useful. So I'd like to actually illustrate, how we can actually solve this problem without writing down any equations by using this concept. So what is the concept of Bloch sphere? The concept of Bloch sphere is basically making use of the analogy between the evolution of the quantum two-level system according to this Hamiltonian, and essentially precession of the magnetic moment in the external magnetic field. This is a model. It can be in any direction. So I just choose my field to be oriented along one direction, and I choose my z-axis to be along this. So, but with the Bloch sphere picture, the nice thing with the Bloch sphere picture is that you can always, find out what the answer is going to be, even for arbitrarily oriented field. Okay, so what's a Bloch sphere picture? So essentially, what we say. So that's the physics of this model. So the physics here is that we consider, for example, magnetic field pointing along one direction, it can be z direction or anything else. And then we ask the question, what if our spin is oriented along an arbitrary axis, say the z-axis, how is it going to evolve? Right? And since we think about our spin as about kind of a classical magnetic moment, so it's clear that if we orient the spin along the z direction, it's not going to precess. So consequently, we will know the dynamics. At the same time, if we start with our spin oriented, say, along x direction, right, then what will happen is that the spin will start rotating around the z-axis in this case. And the angle of this rotation will be precisely the integral of this kind. Right? This will be an integral of the magnetic field required over the time period.
Is there a 2 in the commutator on the right side? Yes, plus.
Which one?
The commutator of S.
This one here?
In the factor of 2.
There might be a factor of 2. So let me okay, but so the point is, this picture, this Bloch sphere picture, is one out of maybe 4 things you need to know about atomic physics to really understand and follow and do the calculations, right? So, be patient. Okay, so this 1 quarter, we covered 1 quarter. So okay, are there any questions about this picture? Or about the stuff which we talked so far? So that's a very, very basic stuff, and you need to remember it when you're asleep. At 3 o'clock in the morning, when you're woken up. If you remember that after this week, that's already good. All right, so with all of these kind of considerations, what I would like to do, also kind of as a warm-up exercise, is to ask a question. So what's going to be a density matrix? What's going to be the evolution of a density matrix? For our spinal car part. So, in particular, what will happen, for example, with the diagonal elements? The density matrix, which are basically populations of the levels, right? So these are essentially probabilities to find the system in a state up or state down. So what's going to be the time dependence of this matrix? Are they going to change in time or not? No, we're not going to change in fact. It's exactly right. So it will stay the same and nothing is going to happen. And one can see it immediately from this block sphere picture, right? So basically, if you started with your block vector, right, oriented in an arbitrary way, but it will just precess around the z-axis. The projection on the z-axis is not going to change, right? So now, what will happen with the off-diagonal element of the density? Is it going to change or not?
That's a phase evolution.
It's exactly right. How does one see this, and how does one figure out what phase?
Okay, you simply the phase that integrate.
Exactly. So what is this density matrix element? Essentially corresponds to quantum mechanical expectation value of this S either of a rising operator, right? Because essentially to quantum mechanical expectation, right? So because right, that's basically when you calculate the expectation value, right? You just take a trace of this operator density matrix, and what you get is precisely this matrix element, right? And so what we will find by using this approach is, and this is a system, right? It's a system density operator, which will be essentially where phi is this thing. Okay, so these are kind of all very basic things which are good to review. But the question which I'd like to now ask is, I'd like to kind of perform the average over this stochastic process, and this will be in some sense equivalent of tracing over the environment in our case. Right? This is a kind of toy model of studying here. So what I would like to do is I'd like to basically calculate the density matrix average over this classical stochastic process, and there will be of course some initial value, but then what I need to do, I need to basically calculate the average over this quantity. So the question is now, how can I express this average in terms of the initial kind of things with which we define this stochastic process? And here we can make use of the fact that this is a Gaussian distributed variable, so with zero mean, right, with zero average. So what this means is that this thing will be equal to something like this. So the reason why you can make this substitution is because we have this Gaussian distribution. So essentially, one way of thinking about it is you can expand this exponent and basically kind of average each individual term. Right? And the first term will be clearly 0. The second term will be precisely this. Right? The third term will be the product of 3 these, and they can be, for Gaussian process, can be decomposed on product of 1 and 2, etc. So, is it clear? Are there any questions? So that's the only kind of sophisticated mathematical step that I want to use. Right? So basically, all what we need to do now is calculate the expectation value of the square of the phase. So essentially, we need to calculate the phase diffusion. So I'm hoping that perhaps this kind of analysis might also be helpful for Bill's lecture tomorrow, if he wants to talk about limits of laser. Because these things are related. Okay, so what we need to do is just to calculate this phase diffusion, and it's actually easy. to do it because we have an explicit definition of this process. Here an explicit definition of this state. Okay, so let's now go back and talk about the stuff that really matters and the reason why I'm kind of going into these discussions at length. So clearly the way how this phi squared will depend on time depends very much on how this beta changes on time. So what I would like to do now is I'd like to consider two opposite cases. In one case, this beta will be very rapidly fluctuating quantity. So in other words, if my block vector starts to precess, it will actually kind of precess in one direction and immediately precess in another direction, and it will kind of start jiggling like this. So I mean, there will be, of course, some variance growing up in time, but this will emerge as a kind of as a result of these many jiggles. The alternative scenario is when this beta evolves very slowly. Right? So in this case, even if it's a random variable, you might consider that during kind of my entire experimental run, this thing is essentially fixed and changed very little. Right? So I can accumulate as a result a substantial phase. So these are these two cases which I would like to consider. And the first case, A, is the case of what is called short correlation time, which also is sometimes called the case of Markovian environment. So what do I mean by that? So what I mean by that here is that this quantity B of t will change on a time scale Tc, which is the shortest energy scale in the problem. So it's much shorter than the time over which I want to look at my system. It's much shorter than this kind of square root of this, variance of B, etc. So how can I analyze a problem like this? So, well, evidently, what I'd like to do now is I'd like to, take my correlation function here and really shrink it to essentially a single point, right? So, this will be kind of, very, short, essentially a step function. So the way how I can describe it is by choosing f of tau to be basically approximately equal to a delta function of tau, but actually I need to kind of multiply it by my correlation time Tc. Right? The reason is that, remember I defined it as to be normalized to 1, right? So just, kind of to make sure that this f of 0 is actually truly equals to 1, I have to multiply by a correlation. Is it clear? Does it make sense? Any questions? Okay, so and then what we can do, of course, in this case, when it's a delta function, what we can do is we can immediately calculate this phi squared, and we'll just use this definition of phi, it's an integral over beta, so I'm going to erase it. So in this case, what will happen is this phi squared, which now involves two integrals, and the integrals over dt, d tau prime, d tau double prime of the so essentially what I can do now is just substitute them to here, and you see that I have a delta function. So when I do one of my integrals, it will kill a delta function, and I will be left with a linear dependence of this phi squared on time. So essentially, this integral, apart from some insignificant factors of 2, will be given by this expression. So what we see immediately is that in this case, when the correlation time is very short, the decay of this off-diagonal matrix element will be exponential. Right? So this thing will decay just with a normal exponential, and this decay constant, which we call gamma, will be proportional to the magnitude of this fluctuating field times this correlation. So this type of Markovian decoherence process is a process which is perhaps one of the most common processes in quantum optics and atomic physics. So for example, spontaneous decay is a Markovian process. The reason why this is a Markovian process is what? Why spontaneous emission? Why does spontaneous emission have a short correlation? What determines correlation time in spontaneous emission? But spontaneous emission is a process in which you start with the atom excited and the photons in a vacuum. And then the atom interacts with your radiation field, and as a result, what happens is that basically a single photon is emitted. So essentially, your atomic state becomes correlated with the state of your environment, right? Which basically, atom becomes entangled with the photon essentially during the spontaneous emission time, spontaneous emission. So why is and it turns out that this kind of Markovian approximation is an excellent approximation for spontaneous emission, as you can, for example, read in Professor Meister. So why is it a good approximation? Come on, guys. Or, even if you're not sure, think, let me make some suggestions. What is the most important property of the photon? What distinguishes photon from?
Masses.
That's right, and?
Quantized.
Yeah, but a lot of other systems are quantized. But there is something about photon which is very, very special. There are other things, spins can be polarized, right? So, what is the most special thing of the photon? What? It's speed, exactly. It's very fast, right? So then think about this, this process involving the spontaneous emission. As soon as a photon is created, it runs away. The spontaneous emission itself takes place on a much longer time than the kind of time scale with which the photon moves. So basically, the correlation time, in this case, of the photon, of the atom emitting in free space, is determined by the speed of light of the photon. So that's why Markovian approximation is an excellent approximation for spontaneous emission. Okay? That's why, if you read Professor Meister's book, you would think that most of the things in life are Markovian. That's not true. No, absolutely not.
If you get old, it's true.
Apart from some philosophical considerations. So as a matter of fact, if I manage to
So, how do you connect that? From there, it seems to me that, when you say Markovian, it seems that the environment is changing.
Exactly.
So in time scale, but how does that connect to a photon moving? Like, I thought the environment is electromagnetic field.
Yeah. So basically, the way how to make a connection is that, the spontaneous emission is accompanied by the change of the radiation field associated with the environment. And this radiation field change occurs on time scale of this kind of, of the speed of light, right? This is true unless you can find the photons in a small geometry. Unless, for example, you have some cavity where the photon can come back, and then it's no longer true. But, you know, it is true in many cases. Okay, so this is one limit, but actually today's lecture was supposed to be devoted to another limit. So this is a limit of the so-called non-Markovian or quasi-static environment. And so in this case, Tc is long. So in other words, let's consider a situation where our correlation time is much longer than the time scale for which I'm doing my typical experiment. And so in this case, what will happen is that basically, you know, I can just set my correlation function here to 1. So I still am dealing with the system which is not completely isolated, because I have this kind of random perturbation, which, for example, if you do experiment many times, can change from one experimental run to another. But in this case, what will happen is that, you know, we can set this f of t equals to 1, and as a result, my off-diagonal matrix element will decay very differently. It actually will decay quadratically in time. Because in this kind of integral, essentially, you know, I just replace this by this b squared, and, you know, just have to integrate twice, so I get t squared. So this is the example of non-Markovian or quasi-static environment. So it's obviously very different from the Markovian environment, and actually, in some way, this is a kind of environment which is more interesting or more amenable to control. So in particular, so let me make a couple of remarks. So first of all, this kind of evolution can be understood as a precession of spin in a random static field. Secondly, so if it's really truly static, what you could do is, if you could somehow midway through the evolution time reverse the precession, then you can really recover your coherence. And this time reversal within the correlation time Tc is a basis for something which is called spin echo sequence. So you can achieve this time reversal using something which is called bypass. So I think this one, I hope I can still discuss with you. So the third option that you have is to try to actually make a measurement on the environment. If the environment really changes very slowly, what you can hope to do, you can use your quantum system to basically try to determine what this value of the field is, right? This is totally impossible in this Markovian field because it changes so fast. But here, we can really try to make a measurement and determine, and then the things are no longer random, right? So, this kind of measurement, or sometimes can be viewed as a kind of cooling of the environment, has a special name. It's sometimes called reservoir engineering or environment engineering. And the final thing which might be possible in this case is that you can say the following. So suppose your environment is now a quantum system and it evolves very slowly, much slower than the system itself. You could say, well, hold on a second, so maybe this environment could be used as a useful resource. So in other words, instead of looking just at the evolution of your system, maybe you can put the quantum information, the qubit in the environment, and hope to extract from it sometime later. But if it's such a slowly evolving system, this might be possible. So this is idea of use of the environment. All right, so these are kind of the basic concepts associated with the kind of system reservoir interaction, system environment interaction, and these are these two basic limiting cases associated with the environment. So what I'd like to do now is, in the next half an hour, talk about the systems, specifically the systems which are this kind of quasi-static interactions with quasi-static environment. But there is time for questions.
In order to realize point 2, does the Hamiltonian have to be even under a time person?
So you are talking about system environment interaction, right?
I guess so, yeah.
No, the answer is no. And while we are at it, perhaps I can now illustrate how this time reversal works. So the best way to think about it is in terms of blocks here, right? Remember, this is 1/4 of the things we need to know. So this is this so-called spin echo idea, and this, of course, spin echo is a concept, one of the very early concepts in MR, which sort of then stored a broad range of knowledge, books, volumes, and so on. But the idea is, so basically the idea is the following. So suppose you want to do an experiment where you, for example, measure the coherent evolution of a two-state system. So, for example, a Ramsey experiment is an experiment of this kind. So what Bill described today in the morning basically was an experiment in which you first start with a two-level system of the spin oriented along the z-axis, and then apply the pulse, parallel two pulses, which rotates it effectively in xy plane. And then, essentially, in the atomic clock experiment, what you are trying to do is you're trying to measure the rate of the precession of this vector. Very, very precise. Now imagine that what you have is not so good clock. So imagine, in fact, that the stuff which determines your precession frequency is this kind of random signal. So, but imagine that this signal evolves very slowly. So what will this mean? So it will mean that in each given experimental run, you will start evolving in this xy plane, and you will pick up some phase phi. So this phase in general will be random, but you know that this field does not change very, very rapidly. So what the spin echo does, it basically inserts an extra pulse in the middle of this Ramsey sequence. So essentially, in the spin echo sequence, the Ramsey sequence is you have pilot 2 pulse, re-evolution, another pilot 2 pulse. So that's basically pilot 2 pulse takes you from the z-axis, rotates you here, and you evolve, then you do another, you convert, and the second pulse converts coherence into population. That's easy to measure, right?
And then it cancels out this extra phase.
Well, hold on a second. So this thing, in this thing you would measure this random phase. Right? This will be affected by that. What the spin echo does, it basically introduces another pulse midway through this evolution. And this is the so-called bi-pulse. So in fact, what it does, it basically takes your spin, for example, and rotates it, say, along the x-axis. So suppose that you evolved, you first started with z, oriented along x, start evolving along this axis, and then what you do, you basically, for example, with a pulse, change your orientation in such a way that you basically make a kind of mirror image with respect to say x-axis. Okay? So what happens then is that before your second period, you are here, and then you continue rotating in the same direction. And then in the second period, you basically pick up exactly the same phase. And this second phase will compensate the phase which you picked up in the first. Right? So as a result, here you'll end up in exactly the same state which you started with, so long as your external field did not change. Right? If your correlation time is very, very long, this exactly eliminates it. So that's the idea of this pulse.
So that pulse sequence has to take place at a time scale much smaller
Then TC, that's exactly right. So if the field starts changing, then some things you will start seeing. So as a matter of fact, this spin echo can be used to make a measurement of correlation properties of your environment, right? As soon as the environment starts evolving, you will see it as a decay of the ecosystem. Okay, so of course conveniently here left, so when is my lecture supposed? It's like 20 minutes. Okay, so basically, okay, let me know. So are there any other questions about this? So this is a very basic kind of material, but you will see it, if not in my lectures, then in other lectures in the school, showing up all and over again.
So you need to know when to apply the middle pulse, right?
So you apply it always right in the middle. So you divide this interval by 2 and apply it right in the middle. And of course you basically want the phase which is accumulated here to be exactly the same as the phase which is accumulated here. Sorry.
Here you are assuming that the E doesn't change.
That's right. So we assume that not only direction, but also the magnitude doesn't change. Right?
And if it changes,
If the magnitude changes, it's already, it kills this ecosystem. If the direction changes, it also kills this ecosystem. All right? Okay, so let me now kind of illustrate some of these ideas on just one example, of one specific research direction. This research direction involves what we call solid-state atom-like systems. So what are these? So basically, these are localized impurities in solid state which effectively behave like trapped atoms, which we can use for research or technology. So essentially, these are this kind of solid-state realization of atomic model systems. And the key is that they can combine, they can be isolated with kind of nanoscale precision within the solid state. And once we kind of apply the tools of quantum optics, we can actually achieve quite good quantum control over the subject. So they as compared to just conventional atoms and molecules, they allow us to explore new parameter regimes. For example, they allow for strong decoupling to photons, phonon spins. They're actually also ideal for the realization of this hybrid quantum system. And of course, we also want to study new applications of the systems, and perhaps I will have some time to talk about it. Okay, just one specific example. In what follows, I'd like to consider something which is called nitrogen vacancy color center in diamond. So this is basically an impurity in diamond, which consists from the nitrogen atom, which substitutes a carbon atom in a diamond lattice, and the missing carbon atom, the vacancy. So together they form a stable kind of molecule-like impurity. And kind of for the purposes of today's talk, I would like to actually make a comparison between this impurity and trap times. So why is that? Well, because similar to the trap times, they actually are optically active. So in particular, there is an optical transition in the red, which one can excite. And one can also, by watching the fluorescence, one can also basically isolate and detect a single sample, much like is done in trap time research. In addition, they have also non-trivial ground state properties, And in particular, in the ground state, it turns out that this system is a spin triplet. So there are 3 states with m sub s equals 0 and 1. And in the absence of external magnetic fields, these states are split by about 3 gigaflops. So this is very similar to, say, some rubidium atom, where you have hyperfine sublevels, which you can then derive with the microwave fields. So basically, what follows, I will tell you a little bit about some experiments which we are doing with these nitrogen vacancy centers, and they essentially amount to having a new look at a rather old but quite unique material. So diamond is actually very well known, most prominently because of its hardness, but also because it has a wide band gap and also it has a very high formal conductivity. But kind of for our purpose, some of these things are important. So in particular, the fact that it's a wide band gap material is very important. And what's also important for us is that you can actually make these diamond crystals extremely pure. So in our experiments, we actually use the diamond samples, which are grown by a process known as chemical vapor deposition. So essentially, this is a process in which in the growth chamber, the carbon atoms are deposited on a kind of cooler substrate, and in the process of that, one can really grow kind of a single crystal, diamond slabs, and which can be extremely pure. So it can basically have, very few kind of dislocations and very few impurities over. And then what we do after that, we actually create these NV centers by just shooting ions of a given energy, into the diamond slabs, and then we subsequently anneal these samples, which annealing causes vacancies to be mobile, and basically the vacancies produced by damage from this ion implantation, they migrate closer to NV center, closer to nitrogens and form these NV centers. So basically this is a kind of, race of NV centers which we can produce is actually an optical image. I will tell you in a second how this was obtained, but these are essentially kind of NV centers which were created through this implantation. So in this case, they're separated by something like 10 micrometers. No, it's created afterwards. So you first start with a sample, and then you bombard them with ions, and then you anneal the sample, and that's how this.
What's the energy of the ions?
So the energy of the ions determines how deep inside the crystal they grow. So, for example, it's basically the rule of thumb. They go 1 nanometer per 1 keV. So 10 keV corresponds to about 10 nanometer depth. So you can easily, this is not a limitation, this is like megaelectron. This is totally standard. So, so experimentally, how do we isolate single centers? So we do it using the optical microscope. So essentially, so this is a kind of the schematic of a typical setup. So it's actually a very simple setup, it turns out. So where basically, we just have an oil immersion microscope, and focus it on the diamond sample, and we basically put a diamond sample. So here, I guess it's a little black thing. This actually diamond sample. So basically, we put a wire across this diamond sample just as a source of microwaves, and then basically just make a scanning confocal image, and we can basically detect this little tiny white spots by zooming on the spots, and by, for example, studying optical microwave spectra, or by measuring lower second-order correlation function, we can really verify that this is a single center, because it produces one photon at a time. It cannot produce a single emitter, cannot produce 2 photons at a time. So that means a second-order photon correlation function should actually vanish at 0 time. So so that's how we isolate single V centers. So this is kind of a technical slide. Maybe I don't want to really go through this, but I would just like to emphasize, so why is a diamond host special here? So the diamond host is special here is because it has very wide band gap. Right? So there's a very big band gap between valence and conduction band of the diamond, and as a result, if you just look at that, so there is basically a single kind of particle orbitals. So there are many of them situated within this kind of band gap. And so what this implies is that basically you can have a localized system where the wave function is localized both in the ground state and in the excited state. So that makes the system really behave like a few level up. Right? So you have basically the ground state which is localized in the excited state, where you just promote some electrons between this single particle orbitals. All of the wave functions are localized. So this is basically a localized object. And so in this kind of situation, what we can do, we can immediately apply the kind of tools and techniques of atomic physics, not just to observing these single atoms, but also to manipulating them. So in particular, what we can do is we can use a technique of optical pumping to spin polarize the atoms in a well-defined spin state. How many of you have heard about optical pumping? So what the optical pumping is a process. So basically, okay, so if you start, for example, at room temperature, which is KT is much larger than say 3 gigahertz. So, and in the thermal equilibrium, what will happen? All of these free states will be populated, right?
Are you going to tell us about how fast the coherence is?
Huh?
Are you going to tell us about how fast the coherence is?
So basically, what the optical pumping does, it basically selectively excites the atoms in some of the states and not in the others, right? And if it selectively excites some of the states, and then the atom decays, right? Then what will happen is that the states which are excited more will be kind of empty more. So as a result, we will create population imbalance. So in this case, and I don't want to go into details, but this kind of selections can be due to polarizations or frequency selections or some other things. And so eventually, what we can do, we can polarize the atom in for example, in m sub s equals 0 state. In addition, we can also use optics to detect the spin state. And the idea is actually kind of very similar to the optical pumping. So what will happen is that if atom in certain spin states is excited more rapidly than the atom in some other spin states, then what will happen is that basically the atom will be more or less bright depending on its speed. And as a result, we can really measure the spin orientation. So this is actually the kind of the example of such a measurement. So essentially, what is done here is that first you spin polarize in the center and m sub s equals 0 state, and then you start driving the microwave transition with basically a square pulse of the microwaves. Then you just change the duration of this microwave, and then what you see is that basically as a function of the duration of the microwave, the center becomes more or less dark, right? And this kind of its brightness following this pulse sequence is determines essentially in which speed state it was as a result of this pulse sequence. So by doing that, we can measure this kind of classic Rabi oscillation picture. And what we see here is that basically, if you look at the kind of time scales on the order of hundreds of nanoseconds, this is really a very nice sinusoidal curve. Now, what Roman really wants to know is that how does this curve, how long does it persist? So it's actually kind of, if you extend it to a few microseconds, what you see that these oscillations will eventually decay. And this decay is precisely the signature of this effect of decoherence. So in our case, this MB center is not in vacuum, right? It exists in a solid state matrix, and there is some stuff around it which affects it, and as a result, destroys this coherence.
That's a good question.
Yeah.
So this time appears to be much longer than the typical decoherence time for solids. Why is that?
So there are a couple of reasons for that. So one of them is that this is a spin degree of freedom. So the charge degrees of freedom in the solid state typically have much shorter coherence times, simply because a lot of charge fluctuations and things which go around the solid state objects, which basically couple much more strongly to charge degrees of freedom. So spin does not couple directly to charge degree of freedom. For this reason is a little bit long. So it is also fairly long for spin. This time scale of microsecond is fairly long, even for spin degree of freedom. And this is connected with several specific kind of features of the diamond as a whole. And this is the features which I'm going to describe. So in particular, the fact that this is very pure in terms of magnetic impurities. Okay, so let's try now to gain some insights and understand what is going on, what is the origin of this decoherence. So the microsecond is long for solid state, but it's short for atomic physics, for example, systems. So it turns out that the thing which causes most decoherence is the kind of magnetic impurities which exist around those in this center. So in particular, I just would like to remind that diamond consists mostly from the carbon-12 isotope. So there are two stable isotopes of diamond, carbon-12 and carbon-13. And in natural abundance carbon, there is basically 99% of carbon-12 isotope, and this carbon-12 isotope has 0 nuclear spin. Carbon-13 isotope, and there is 1% of which in this natural abundance, has a nuclear spin 1/2. So this is the most common magnetic impurity. So basically what happens is that if we really succeed in kind of getting rid of all other impurities, so these nuclear spins play the most important role. So in particular, so actually both nitrogen nuclear spins, so nitrogen also has nuclear spin 1, but it's just one of them, and this kind of 1% of carbon nuclear spins are the magnetic impurities which cause this kind of random perturbations. So there might be some other impurity electron spins on that, if you have pure samples enough, it's not. So okay, what is the physics? How can we describe the system? And that goes back to this discussion which we have. So let's call the electronic spin S, and then the Hamiltonian, which corresponds to this electron-nuclear interaction, is this kind of Hamiltonian shown here. So this is basically kind of a hyperfine Hamiltonian, which corresponds to nuclear spins, many nuclear spins, projecting the magnetic field at the position of the electron spin, and vice versa. So the electronic spin creates a magnetic field, which nuclear spins feel. So what's the connection between this Hamiltonian and the model which we have considered earlier? Well, what you could say now is the focus. There are many nuclear spins in practice, and the nuclear spins is the object which, even sort of, it's very hard to polarize them. So particularly at room temperature, they will be oriented all in a random direction. So what I could say then is that we can rewrite this Hamiltonian as in this kind of form, where essentially nuclear spins, due to their random orientation, produce some kind of random magnetic field. And this random magnetic field affects this electronic spin. So this is a real quantum model, but the actual effect from this model will be very similar to what we discussed before. So this is like a random magnetic field at the point of the electron. And so, in fact, if you calculate the magnitude of this random magnetic field, then what you will basically find is precisely this kind of 1 microsecond decay time. Right? So that's precisely this T2 star time which we have measured. And you can say, well, okay, that's the end of the story, because it's a solid state system, you have some random perturbations, but actually it turns out that it's not the end, it's actually the beginning of the story. And the reason is that the nuclear spins themselves evolve extremely slowly. So if you think about nuclear spins, they they don't really interact with anything. So we have very tiny magnetic moments. So, the evolution is extremely slow. And for this reason, this is an example of eminently non-Markovian environment. So this environment which has very long coherence time. And this nuclear spin is actually a very interesting object. In fact, it can be used as an important resource. So here is some kind of, more insights into this hyperfine coupling of electron and nuclear spins. Of course, hyperfine coupling is common to most atoms, right? Most atoms have electron spins and nuclear spins, like rubidium, for example. But the point is that, in rubidium atom, there is just, kind of few of nuclear spins, and there are, there is maybe one electron spin. So here we have an electron spin which interacts with many nuclear spins. But we can consider these interactions as a kind of pairwise. So we can say the following. So our electron can be in two states. It can be in a state with zero magnetic moment, or it can be in a state with magnetic moment plus minus 1. And if it's in zero magnetic moment, then it will, not cause any field at the position of the nuclei. But if it's a state 1, then it will cause hyperfine spin. So basically, for this, for this case, and if we just have one electron spin, one nuclear spin, so here is a kind of the energy level diagram that we will have, right? So we will have basically two manifolds, m sub s equals 0 and 1, and in the manifolds m sub s equals 1, we will have this kind of hyperfine spin. Now, this by itself is not a real big problem, in that, so long as these nuclear spins are fixed, if they don't change, then what will happen is that basically you just get this kind of static shift transition frequency shift, right? So for example, spin echo will be able to undo it. However, in practice, the nuclei will start to evolve, due to external magnetic field or due to the interactions with each other. And, as they start to evolve, that's a process which really causes entanglement. Causes entanglement between electronic and nuclear spin degree of freedom. And then, in addition, if you now consider many of these nuclear spins, that's where this decoherence really comes from. That's the origin of decoherence.
Are you counting the fact that they're also vibrating?
What?
They're also vibrating, right? The R sub J is changing.
So there are in principle, there could be in principle some vibration effects, such as photons being present. However, in this kind of spin interactions, these effects are extremely negligible.
So
We ignore them, and this is in part because diamond is extremely stiff. So that's okay. So spin echo turns out to be a very important tool here, because on one hand we can use the spin echo to decouple our electron from nuclear, but actually it also, the spin echo turns out to be a very good spectroscopic tool. By doing spin echo experiments, we can actually study what's going on in our environment. And the idea, as I already discussed, is so you start with a power 2 pulse, and you let this electronic spin precess around some axis. And then in the middle of evolution, you just change the direction of this precession, and basically, if the environment is static, the spin should come back. So spin echo signal is only sensitive to changes in the environment, which happen on this time scale of the echo, and as a result, it can be used to study the dynamics of the environment. So actually, the typical echo we observe is kind of complicated in the first one. So this is a kind of the typical echo that one sees if one does these experiments in this center. So there are a couple of features here. So first of all, spin echo clearly has a big effect. So in fact, the time scale in which the spin echo can be observed, even in this kind of natural samples, is like more than 100 times longer than the Stiglitz time. So which is really a statement that the environment really does have long lived. But in addition, what one often observes is not just a kind of monotonic echo decay, but one observes this kind of kind of periodic or sometimes non-periodic oscillation. So where do they come from? So they must come from some kind of periodic evolution of the environment, right? So in fact, this kind of periodic oscillations is very easy to understand. So these periodic oscillations turn out to be due to more precession of the carbon-14 nuclei, right? So because if you do the experiment in external field, the nuclei precess around this external field. So they have some dynamics, but this dynamics is periodic. So if you time your echo such that the nuclei make precise evolution and come back, then your echo is perfect, right? And that's this kind of periodic evolution. Actually, if one is careful and one sees that there's something here which emerges kind of like a noise, it actually turns out that it's not quite a noise. There is actually some useful signal. So in particular, so if you study these pictures for a while, then you can really kind of reconstruct the local environment, local magnetic environment of electrons. So it turns out that the environment is a following. So first of all, you have this kind of far away carbon-14 nuclei, which introduces decoherence and introduces kind of echo modulation. But actually, it turns out that there are some nuclei which are kind of special, and these are the nuclei which are close to the electron. So their wave functions mix with the electron a little bit more, and as a result, they actually precesses a little bit different frequency. So, and this kind of the nuclei which are coupled stronger can actually be isolated spectroscopically. You can, for example, individually address them and use them as a resource. So, okay, so maybe this is kind of a good point to stop. Let me just say that kind of based on all of this, what are the current efforts in this field? So, on one hand, researchers are using this pulse decoupling, this very common technique. So, spin echo and its variation, one can really push the coherence times to something like milliseconds. At the same time, you could say, okay, so since we understand where our coherence comes from, maybe we could do something like with materials engineering to get rid of this decoherence. And it turns out that actually it is possible to grow the diamond now from isotopically purified carbon-12 carbon atoms. So there you just reduce the density of magnetic impurities. And there you can, for example, increase this T2 star by more than a factor of 100. And actually, with the help of echo, you can also get coherence, which is basically something like few milliseconds. Because this T2 time of the environment is very long, it turns out that you can actually make an instantaneous measurement of this nuclear magnetic field, and as a result, kind of use a feedback procedure to actually really compensate for this random magnetic field. And this is an example of the environment engineering, which you can do either for measurement or through cooling, much like laser cooling of atoms, you can cool nuclear. So maybe I will talk about a little bit tomorrow. And then finally, there is a topic of controlling and using nuclear spins. So it turns out that if you use some of these proximal nuclear spins, you can really do some wonderful things. For example, we can actually make the room temperature quantum memory, which lasts many seconds. Right? And it's an example of the use of this. So I guess I've used up my time, so maybe I will talk about some of these things tomorrow. Since I created some appetite, hopefully, for that.
So I think we owe Misha a special thank for taking the time he wanted to talk about his hard physics, to really go back through all these things that we all need to understand. So thank you so much. This is really, really highly appreciated. And we will have dinner where you can ask an infinite number of questions. All the questions we ask you to answer, now he will listen to the answers over dinner, okay? So you're not off the hook, I hate to tell you. But I think now we should probably stop for a few minutes. As I told you, we are going to have a special presentation by Dr. Winner here about what it will be to become a faculty member, to become Misha's major competition, which is a big challenge, by the way. And so we are running a bit late, but let's try to come back again, let's say in 20 minutes. And the bad news is that Dr. Fine has a very modern car, and the computer in his car died, and if his computer died, his car won't start. So Dr. Fine will not be with us tonight, but Dr. Hill is here, so we'll have this nice question and answer after your talk. And what there's a lot of information we'll give you tomorrow about the outings of Saturday and Sunday, but we'll keep it for tomorrow, so to make sure that you are here. And again, breakfast tomorrow will be at the 9:30 Boston time.
I think I corrected.
Okay, thank you so much, Lisa.